Hi everyone, I hope this message finds you well. First of all, I want to express my deepest gratitude for your patience and understanding during my recent absence from YouTube community. I know it's been a while since you heard from me with all my wonderful videos, and I want to take a moment to explain why. The truth is, I have been on a journey on my master's degree in data science, and it's been an incredibly rewarding experience for me and challenging as well, and it demanded my full attention and dedication. While I've been away, I've missed our interactions dearly. Your support and encouragement have always meant a lot to me, and I'm motivated every day by it. But now, I'm thrilled to announce to you that I'm back with more interesting videos. And I hope that you will enjoy these videos with me, and I promise that upcoming videos in my physics practicals and these lessons ongoing will be worth your while. Thank you for sticking with me and your unwavering support. Now, let's go back to today's video. So in this lesson, we'll be looking at chemical reaction. So, what comes to your mind when you hear the phrase chemical reaction? Many will think of bubbling beakers, fuming flasks, maybe even a famous baking soda and vinegar volcano, as you can see in the picture. But that's not just what chemical reaction is all about. So let's continue. But it turns out that chemical reactions aren't just experiments in the laboratory. They are all around us, happening all at the same time. So in engines, in plants, we can see chemical reactions happening, even in industries. Alright? Now, understanding chemical reactions provide all sorts of insights into many aspects of our lives. In this course, we'll be looking to explore the bolts and nuts of chemical reaction. So let's continue. So here's a chemical. It's called sugar or glucose. Glucose or sugar is made up of 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. That's represented in the diagram. Alright. So atoms are building blocks of all matter. Atoms come together in countless arrangements and ratios, but when they come together in exactly the same way as shown above, we call that a molecule. In this case, a molecule of sugar. So in a single teaspoon of sugar, there are billions of molecules, but in each one of all the atoms, they are arranged the exact same way in space and in the same ratio. Remove any atom or change the way they are connected to each other, it will no longer be glucose anymore. So when we talk about chemistry, we need to talk about some things that has to do with chemistry, such as chemical reactions. We need to build our vocabulary, so we talk about reactions. In a reaction, we have what we call the reactants and the products, as we can say in the diagram. So reactants, they react and they form the products. So all reactions have a start and a finish. Anything present at the very start is called a reactant, and what we end up with are called the products. You can see the arrow that shows the direction from reactants to products, from left to right. Let's continue. Chemistry is ultimately a game of molecules, changing and transforming in grand dances we call reactions. So during reactions, there are some things that change while others remain the same. So if we look at this reaction we can see here, so there are things that remain the same and there are things that change. The things that change is the spatial arrangement of the electrons. The spatial arrangement of the electrons change, but the identity of the atoms don't change. The number of atoms don't increase or reduce. What changes is the spatial arrangement of these atoms. So that constitutes what? The reaction. So in the course of this reaction, as you can see, now what is not changing? It is the identity of the atoms involved. the identity of the atoms involved are not changing, and that's correct. So let's look at this. So that's the explanation I have made all this while. So spatial arrangement of atoms, okay, change, whereas the identity of the atoms, in this case we can see is the color of the atoms, they remain the same. All right, so let's continue to our video lesson. So chemical reactions cannot change the fundamental identity of atoms involved. For example, no reaction can turn lead into gold. So what exactly determines the identity of an atom, if we ask? Okay, let's look into that. So to understand this difference, we need to zoom in and explore what atoms are made of. So atoms are made of what? They're made of electrons that revolve around them, and there are a nucleus that constitutes the core. So we have the nucleus and the electrons. The electrons exist in a cloud around the central nucleus. So the nucleus here bears the core identity of the element. You will see that. So let's continue. So carbon atom, hydrogen atom, and aluminum atom can be seen in the pictures above. All right. So atoms are overall neutral, but a single atom can contain many negatively charged electrons. Yes. So what does this imply about the nucleus? So it simply means that a nucleus must bear a positive charge equal in magnitude to the total charge of the atom's electrons to make it electrically neutral. So that's that. Atoms overall are neutral. A single atom can contain many negatively charged electrons, as we said. So that's that. Electrons, the charge of the electrons has to counteract the charge of the nucleus. Now, nucleus at the center of atom is so stable that it can't be changed by chemical reaction. So nucleus can't be changed by a chemical reaction. This is because chemical reactions involve electromagnetic force, which is weak compared to the strong nuclear force that holds the nucleus together, as you can tell by its name, nucleus. So this means oxygen atoms will always remain oxygen atoms, and hydrogen atoms will always remain hydrogen atoms, even when they are involved in a chemical reaction. So the nucleus bears the identity of the atom. So what is changing then? Let's continue. So as we walk through ever more complicated examples of chemical reactions, a trend will emerge. Electrons. Electrons is the end game. So when we boil down even the most sophisticated reaction going on in industry, nature, and our bodies, it comes down to electrons. So understanding where the electrons are in molecules and where they tend to go is one of the most important tools that allow chemists to make useful and accurate predictions about reactivity. So chemical reaction is the game of electrons. Electrons change hands. Interesting, right? For this course, reactions are all about electrons, but what sort of things happen to atoms during these reactions? For now, we won't concern ourselves with the ongoing of atomic nuclei and the rest of them. To keep things simple, we'll continue to treat atoms as simply as spheres for you to understand appropriately. So let's continue. Suppose that during a chemical reaction, a neutral oxygen atom were to gain 2 additional electrons. Now, let's look at this question. What's true about the new state of the atom? You have so many options there. What do you think? The atom has been transformed into a different element. The atom is still oxygen but with a net negative charge, or the atom is still oxygen but with a net positive charge. So the answer there is the second one. So the atom is still oxygen but with a net negative charge because it has gained 2 extra electrons. So the opposite is true when it comes to losing electrons to become a net positive charge. So for an oxygen atom whose symbol is O, we could represent a double negative charge like this. So O with an exponential 2 minus, showing it has gained a net negative charge. That's it. So let's look at other simple transformations. Sodium chloride is a table salt, represented by the formula sodium chloride, NaCl. Okay, so now when we split this compound into two, because they are bound electronically, what happens when we split them apart? Let's see. So we can do that by what? Adding water. Okay, when we add water to salt, the salt dissolves in the water, splitting apart into sodium and chloride ions. Remember, I use the term ions, but it simply means sodium with a net positive charge and chlorine with a net negative charge. So it simply means that chlorine gained electron from sodium, making sodium more positive and chlorine more negative. That's that. So let's continue. Now, of course, even without much experience reading chemical equations, you can see this equation: sodium chloride and water, okay, forming sodium ion, which is sodium with a net positive charge, and chlorine ion, with chloride ion, which is chlorine with a net negative charge. So it simply means that when sodium chloride is split into two, we have sodium ion and chloride ion. So that shows you that there's an exchange of electron, and that's that. So let's look at this. So what can we say about the amount of charge that exists before and after the reaction? So we have sodium chloride as a whole, as a molecule, and when we split them into two, we have sodium ion and chloride ion. What happens to the total charge? Now, the first one says the total charge on all the components is larger before the reaction. The total charge on all the components is the same before and after the reaction. The total charge on all the components is larger after the reaction. The total charge is the same. The only thing that happens is that before the reaction, they were together, making it neutral. And after the reaction, they split themselves into their respective components. If we still combine them together, they will still be what? Neutral. That's that. Alright. So the idea that the total charge of all molecules has to be the same before and after reaction is one fundamental principle of chemistry. So one fundamental principle of chemistry is that the total charge before and after a chemical reaction has to be the same. So what this means is that while electrons can and do change hands during the course of reactions, what they don't do is disappear out of thin air. That's what they don't do. Okay, so that's that. That is to say, if an atom gains electrons in a reaction and thus has more negative charge than it had before, we know two things. First, the electron had to come from somewhere, and second, whatever atom that lost the electrons will end up with more positive charge than it had before. As simple as that. So this principle is very important, and we'll revisit it later in this course. So it's a game of electrons. Chemical reaction is a game of electrons. So we talked about understanding chemistry by examining the behavior of atoms, and particularly electrons that dance among them in a fascinating choreography we call chemical reaction. So that's what we've looked into so far, and how the atoms combine themselves to form molecules. So below is a representation of another chemical reaction, this time undergone by a molecule of our friend glucose from before, the hydrolysis of glucose. So forget about the complication of the reactions here. So in this glucose hydrolysis, nothing changes. The only thing that changes is the spatial arrangement of the atoms. The spatial arrangement of the atoms is what changes. If we count the number of molecules there, it remains the same. So we've come to the end of this video lesson for today, and I hope you enjoy this wonderful lesson. We will continue from this. This is a series. This is an introduction into chemical reaction, and I hope our subsequent videos will be more interesting. We guide you into the world of chemical reaction. Thank you so much.